Welcome everybody to our third community research call. The community research calls are our sort of public-facing meeting where we give updates on the exciting progress that's happening at Manifold, as well as places where there are open opportunities to contribute, new projects, and then also org-wide updates. So it's a jam-packed session. We have a full docket for you today. So we'll go ahead and jump right into it.
Great. Yeah.
Take it away.
Fantastic. So I'm just going to take a couple minutes here because we have lots and lots of project updates. But I wanted to motivate for many of the folks who are attending today's call are new and haven't maybe heard of Manifold or been as familiar with Manifold in the past. So the question is, what is Manifold? So I'm just going to spend a couple minutes on that. So Manifold's really a new kind of research lab. So we've been thinking, and we've existed for a while now, but over the past year, we've really evolved into a research lab. The way that we frame it is a research lab for the 21st century. So the idea is to be able to work on really large-scale thesis-driven research projects that you're also able to coordinate with huge amounts of async sort of collaboration. So that can be with open source groups, academic groups, and the like, and also engage in sort of structured collaborations and partnerships. So trying to combine useful characteristics of modern day industrial research labs, as well as the kind of traits that you see in open source organizations and academic groups. And we really think of this as a very long-term experiment. So we've been, maybe you've seen that we've been growing pretty fast, and we want to continue this. Next slide, please. And to give you an idea of what that's starting to look like, so as you all can see and know, if you're a part of the Discord or you tune in through our research logs or community research calls like this one, we have this large established asynchronous research community, which has, I mean, representation from some incredible places, right? We have incredible sort of indie hackers and people building novel machine learning projects, but we also have very talented researchers, postdocs, faculty members from various incredible universities and programs, who all sort of collaborate in a sort of asynchronous manner in this community. And then we also have a core team of really talented researchers and research engineers focused on advancing several sort of thesis-driven projects, many of which you're going to hear about today. And so we call that the OS research team, and we also have an operations team. And the way that we are trying to advance research is to be sort of as opportunistic as possible. So I think we lost the slides. Yep, there we go. Perfect. And so we do this in a very sort of mission-driven way. We interact concretely with academic labs, with different open source groups, with groups in industry. We also have sort of sustained by winning grants, and it's also mostly a volunteer organization. And in the near future, we hope to start to bring on some full-time team members as well. And notably, we also have a focus on driving innovation all the way from fundamental research, which is really our main what we do, but also trying to set that research up to live longer. And if it is something that's truly valuable and can be used to drive value in the real world in some way beyond a paper or a release, which is of course inherently valuable on its own, we want to figure out how to do that in the most value generative way possible. So that can take the form of spinning off nonprofit organizations to support that research. That can take the form of just supporting large scale open source artifacts and projects and software. And that can also take the form of venture spinouts, so startups and things like that. And we actually sort of recently did have our first spinout, which is exciting. We'll talk briefly about that through the course of today's presentations. But we're really excited about this. We have awesome collaborators from places like MIT, Georgia Tech, Harvard, Bloomberg, Meta, tons of places. And so we're excited about the future. And today you're going to get a flavor of what that research really looks like when you work in this kind of new, almost network-driven way. Next slide, please. One of the things that we're kind of proud of, and we are trying to improve all the time, is how we engage with the world. So, the world, especially in machine learning, this is apparent. The world of research is moving very fast. It's moving in ways that are markedly different and feel like a step change versus what the standard mode of research and the standard sort of infrastructure and established patterns of engagement have been historically, which is, publishing papers at different venues, long lead times on research. of course, when you have this sort of very fast frequency, but also mission driven type of organization and collaboration emerging, you start to move in a different way. And so some of the things that we've been trying to do is, first of all, we ship research really fast. You'll hear a lot about that today. I'm sure a lot of the teams can testify to that, that it's pretty intense and we enjoy that. We also totally work in the open source and engage with the public. So our roadmaps and project tracking and everything is like on GitHub. We try to make it as transparent as possible. One of the challenges is we work on really serious research, so it's hard sometimes to figure out the right ways to sort of enter and contribute in an asynchronous way, but we're trying to improve that as well. We engage primarily through Discord, which is a very opinionated platform, and a lot of people, wouldn't necessarily think that Discord is a great place to have a formal, large-scale research institute like this, but we've been working well on it. And then we have these really fast patterns of interaction. So things like research logs, which we send out every 2 weeks, which are even more incremental updates than what you'll see in the CRC today. And then, of course, CRCs, which are this event series that happens roughly once a quarter, where we get to do a showcase on sort of the different updates around the different research directions that are happening at Manifold. And then finally, recently, we launched the Frontiers seminars, which are invited talks from some of the best researchers and technical leaders in various fields as they pertain to some of the interests and directions that Manifold is undertaking, and also adjacent ones. And those have been super exciting. So we have a bunch more of those, and you'll hear more about those in the future. But I think that's the perfect segue. So we're going to jump into active project updates, and we'll have more on the organization at the end of today's talk. So I guess we'll go ahead and get started. So actually, I'll be the one introing the multimodal action models. Can we go one forward? So this project, many of you have heard of, it actually started with trying to reproduce a model that came out of DeepMind a few years ago called Gato. And so the theme behind these models, all the way from Gato a couple of years ago to now, a bunch more models that you're starting to see, is trying to enable large multimodal, usually transformer-based models to be able to spit out reliable actions, sequences of actions, to be able to engage with some sort of environment. And so these models are starting to be termed VLAs, and it's pretty interesting actually. In the past 5 months or 6 months, there's been more development in this area than there has probably for the past couple of years. And a lot of what these models look like is training very large scale multimodal foundation models on tons of different kinds of multimodal data, and then applying them to the robotics sort of domain. And this is something that we're super, super interested in. We have a lot of work going into this, and we'll sort of touch on a couple different aspects of this in the next few slides from a couple of the speakers. But I want to note that we also will very soon have an update on larger scale VLAs that Manifold is building in collaboration with some of our sponsors and spinouts. So next slide, please. Eric, I think this is all you.
Awesome. So hello, everyone. I'm Eric, contact info up in the top right. And as Harsh was mentioning, Gato, that's what I'll talk about. I'm working on a Jupyter notebook, a more simplified, clear, understandable version of Gato with the goals in mind as described here on the slide. Not focusing on runtime or eval performance, but trying to make it something that is understandable and clear. With the idea in mind, I see a lot of people in Discord asking how they can contribute, how they can get started. And I want this notebook to be a good jumping off point for people who want to get started. In addition to that, I hope it's going to be a good place to jump off to more interesting and serious research, because I think it's a lot easier to explore and extend something that is simple and understandable than it is to explore and extend something that's been thoroughly optimized for scale and performance. So if you go to the next slide, you can see an example of what the notebook looks like. A lot of cross references to the paper. So ideally, you're going to read this in tandem with the paper, play with it, run the cells. And one goal here is minimal dependencies. I want there to be no magic in this. So if you want to explore what patch position encoding is, I know that's not like a detail that was introduced with the Gato paper, but Gato uses it. So let's see exactly what that looks like. Another goal of this is rapid iteration speed. So on the next slide here, you'll see small data sets are really useful whenever you're sharing these notebooks on places like Google Colab or any ephemeral environment that spins up and down. You don't want to have to wait, up to hours for some of these data sets to download just to run a quick experiment, just to explore, to test something that somebody wants to show you. So where small data sets didn't exist, I'm trying to create those, which is simply taking a data set like the OKVQA data set from Allen AI that's 12 gig, slicing off 100 or so samples and uploading that to Hugging Face so it's easy for a collab notebook to just download that data set in a few seconds. Along with the minimal dependencies, you don't want to wait for a really long pip install. So that's the goal of Minigato. You can find it in the Neko code base. There's a subdirectory in the Neko code base where I've been working on this. It's still under active development, so expect links to break, the code to change day to day. But I really encourage people to get involved and yeah, and see where we can take this.
Great. I think Pranav, you can get us started on this on Multinet, right?
Yep. Can everyone hear me?
Yeah, we can.
Yep. Hey everyone. Thanks for coming for the third edition of CRC. So nice to see everyone. And for a lot of you that joined the previous one, you must have already seen the next slide. And so I just wanna can we just go on forward, please? Yep. So I just want to recap what exactly Multinet is, what the thesis behind it is, and also like kind of an introduction to folks who are being introduced to the project for the first time. So really our thesis with Multinet is that um, if we can train, a unified large model on, high quality web scale multimodal data, as well as sequential reward-based action trajectories, which are typically in the form of reinforcement learning and robotics data, we think this will result in an entirely new class of foundation models that are generalists in the truest sense, and also like these are models that can complete long horizon complex tasks with planning, reasoning, and reliable completion of actions, right? And in turn, like because of all these characteristics, they can also provide a really good foundation for a lot of the agentic workflows that most of the AI community is looking for right now. In terms of there's a lot of entrepreneurial ventures around this as well, and research too. So the major goals with this project is that if we do want to build something, a model of this scale, the biggest bottleneck is obviously high quality data across all these various modalities, tasks, environments. So one of the biggest goals for this project was to build the largest open source vision language and control data set. And here control typically refers to reinforcement learning and real life robotics data. And once we have this data set, we also do want to evaluate the current state-of-the-art models on this kind of generalist data. So a challenging benchmark that kind of shows how well today's models do on this kind of data. And then eventually we also do want to utilize this generalist pre-training and knowledge about completing actions across a variety of different environments and transfer them to software environments where we can actually, complete workflows that are useful for like developers or anyone else working in the software space. And we do have projects spinning up around that, and we'll probably talk about that later. The next slide, please. Yep. So on the dataset front, what we have with Multinet is that we've consolidated, pre-training scale, like it shows in the slide, around 70 terabytes, several trillion tokens of fully open source vision language, reinforcement learning, and robotics data. And this data basically spans across a wide range of categories, visual question answering, navigation-based control, image captioning, and just a bunch of different tasks and data sets. And you can find a comprehensive list of what is included in the V0 of Multinet on our GitHub. All of this is documented completely in the multinet repo. We usually track our progress using the issues on GitHub. So you can always like take a look at what exactly the list of data sets is for V0. And one major contribution that we did want to make to the community is that as we were working on this, on the dataset front, we realized that a lot of reinforcement learning and robotics data come from a variety of different sources and are usually they're usually in like many different formats. And they have archaic docs and not very well maintained. So a big contribution that we really thought would help was that we could translate all these datasets into a unified format and a widely used format that could easily be, loaded for any purpose, fine-tuning, inference, pre-training, whatever it is. So we've fully open sourced the code that helps you easily download any or all the datasets in V0 of Multinet. Um, and also like simplified code to translate all the control datasets to a unified TensorFlow datasets format. Um, and TensorFlow being a widely used framework becomes very easy to use all the control data in multinet for whatever purpose you want. Yep, next slide, please. Yeah, so we've been apart from like consolidating the data, translating it, open sourcing the code for all of that, we've made a bunch of progress on multinet. On the profiling front as well. So the first like data set in multinet V0 that we picked to kind of evaluate the performance of the current state-of-the-art models is this data set collection called OpenX embodiment. So OpenX was an effort led by DeepMind and was a collaborative effort across a bunch of different universities and organizations, and basically has tons of real life robot trajectories. And these are usually in the form of observations, actions, rewards, the images from a variety of different cameras, natural language instructions. And it is a highly complex and varied dataset collection just because a lot of this data is collected from a variety of different embodiments, robots itself, tasks, and environment descriptions, all of that. It's just highly varied, but it's a really big contribution in the community because I think it's one of the largest open source real life robotic data set. And so the models that we did start off to kind of profile on this data set in Multinet V0 are obviously like one of them is the state-of-the-art vision language model GPT-4, and then also a state-of-the-art vision language action model called OpenVLA, and then an open source implementation of Gato by the Hugging Face team, which is the jack of all trade models at the GAT. Um, and so when we did want to profile all these models on the OpenX embodiment data, I think a considerable amount of work went into kind of adapting these to even work on these data sets. Because, for example, JAD is only the only control task is it's fine-tuned on, or actually pre-trained on, are very specific tasks, gym-based Atari or Mojoko environments. And with OpenVLA, it's fine-tuned on a very small subset of OpenX. And obviously GPT-4 is fully pre-trained for only vision language data. So like architectural modifications or building entirely new frameworks went into adapting these models to be profiled on OpenX. And we'll be talking more about that in the coming slides. And one uh, one important another important like research question that we did work on was how do we evaluate these models on a data set that's purely offline reinforcement learning trajectories of observations, actions, rewards. We don't have access to the actual robots. We don't have access to environments like gym. So what really is a metric that could reflect the performance? And we kind of landed up on a mean squared error between the predicted action of the model at a given time step and the ground truth action. So this kind of measures how well the model is able to predict the action to take in the current environment, given the current time steps, observation states, image, natural language instructions, and really how well it does. And another metric that we're tracking is at the end of an episode on the last time step, how often does the model take the right action to, successfully complete the episode? So these are kind of the metrics we're tracking. We're actually well underway in this profiling effort, and we have a bunch of results, which we will be sharing as a part of our release with Multinet. Next slide, please. Yep. So I'll be talking about JAT, and then Kyle and Locke, who've been doing some incredible work in this project as well, will be talking about the GPT and the OpenVLA effort. So JAT, like I said earlier, was jack of all trades, kind of like an open source implementation of Gato by the Hugging Face team. It's a singular like neural network architecture that's based on Luther AI's GPT Neo, and it was mainly it's quite a small model, around 100 200 million parameters or so. That's mainly been trained to handle really only two categories of tasks. So one is text-centric tasks, and one is like sequential decision-making tasks, which is basically control that we've been talking about. But being a small model, it's only been trained on a very small set of tasks. For control, it's just Atari, Baby AI, Majoko, MetaWorld, and for vision language, 2 or 3 data sets. So with Multinet, what we really wanted to do is adapt this, existing generalist model to OpenX. And like I said earlier, that took, considerable amount of work just to like adapt it to a completely new distribution of data than it's been, compared to what it's been like pre-trained on. And also the way JAT is evaluated is that because they only train on a super small set of gym-based control tasks, they're evaluated by testing the action predicted by the model in the environment itself. And so that's how they get their feedback and the metrics. Since we can't do that with OpenX, we had to kind of like adapt it to do zero-shot inference on offline RL trajectories. And what we've been seeing is a majority of the profiling effort of JAT and OpenX is actually complete. And what we've been seeing is that it performs quite poorly, as we expected, with high MSE values and nearly a 0% action success rate. So all of these results will be coming soon. And we'll be sharing it with the broader community, and we're open to any kind of feedback. But yeah, this has been an exciting effort. I think I'll let Kyle take over on the GPT front now.
Okay, next slide, please. Yeah, hello everyone. My name is Kyle, and I'm currently contributing to Multinet project. So I'm going to talking about a little bit more of GPT-4 profiling on OpenX. So for the release of Multinet v0, we are also profiling GPT-4o, which is the most famous vision language model these days. In addition, unlike JAT, it is a closed source model that can be accessed through OpenAI's API. So the most important thing to consider when dealing with GPT-4 in this project was that it has not been trained on the control tasks. Maybe the pre-trained data might include some text regarding the reinforcement learning, but eventually it is a language model, and it is not for explicitly performing the RL tasks. So while it can be adapted to various tasks without changing the model architecture or implementation, but also it should be controlled very carefully to get the behavior we want. I personally say this is a trade-off between flexibility and controllability, but anyway, the model does not know what exactly it is doing, such as what is the goal of the task, what is the input and output represent. Also, the output format is not fixed because it just generates text responses. But we only want to get the structured action output, not some free-formed language output. So most of you have heard of the word called prompt engineering, um, where we should instruct the model, a language model, clearly and specifically to use it correctly. We should let the model know the goal of the task, description of the environment, the explanation for each input, and how it should generate the output in terms of the format and values. Next slide, please. Yeah, so this is just an example of the instruction prompt we are using for GPT-4. I'm not going to say this prompt is perfect because there are tons of research progresses on how to instruct the model in a complicated task like this. This is just an example to show what information we are currently putting into the model for this benchmark. You can see that first there are some sentences to elaborate the environment, the main goal of the task, and what object exists in this environment. This will help the model understand the current state more clearly. And then the action space, because we want the model to generate the actions that fit into the restrictions in each data set. So we are giving the verbal description of each action and the possible values. If an action is continuous, we give the minimum and maximum values. If it is discrete, we give the option like here, yes or no. Uh, then we give the output format. Since all OpenX datasets action format is a vector, so we require the model to generate a sequence of the numbers, and each number would be the actual value of each action as we saw here. Um, and we also include the additional explanation of the observations. For example, in this task, there is a vector called robostate. So this part elaborates what each element represents. So overall, this prompt is put into the model always, and these specific parts can be obviously replaced depending on the task or data set. Next slide, please. Yeah, so now this is a simple diagram of how we are using GPT-4o in this benchmark framework. This can be extended for any other models later. But for now, I'm going to go through focusing on the GPT-4. So first, the dataset model deals with all dataset specific logics. Here, OpenX model uses the data loader specific to OpenX dataset and fetches the batch from it. The batch contains the various inputs such as images, text descriptions, or vectors like the robostate we saw on the previous slide. And it also has the labels, the action produced by an expert agent. The OpenX model also generates the instruction prompt using the predefined environment descriptions and action spaces and gets the prompt just like the one we saw on the previous page. Now, a dataset model can have modality model, which deals with the modality-specific logics. Here, GPT-4 is a VLM, so VLM model handles the batch and converts each input into the format that VLM can take. For example, if the input is an image or text, then it just passes the input as it is. But if the input is some data structure or other than image or text, like a map or a list, then it converts the input into a string so that it can be understood as a text by the model. Finally, the OpenAI model wraps up all of this information, preprocessed input and instruction prompt, and hold all this information and calls the API to get access to the GPT-4 model. The model gives us a text output. Now VLM model converts the output again because we want a vector format action output. Finally, OpenX model compares the output and label to calculate the accuracy. These frameworks can be extended to any other models by replacing the modality model or OpenAI model, and this will be improved over and over again while progressing the project. Yes, I think that's everything from me.
Okay. Thank you, Kyle. Can everybody hear me?
Yeah, we can.
Yep.
Oh, perfect. I'm Locke, and I've been working on the OpenVLA eval and profiling effort. So I'll just start with a brief overview of the OpenVLA's model and architecture. So OpenVLA is a 7V parameter vision language action model built on top of Prismatic, and it was trained on 970,000 data from OpenX, and it outperforms larger models like RT2X, which has 55 billion parameters, and it's almost 7 times smaller, and it's able to achieve like 16% um, higher absolute task success rate. So in terms of the architecture, OpenVLA has Dino v2 and SIGLib backbones. They takes in the images and then convert them into embeddings that capture both spatial and semantic features in the scene. And then they have a custom multi-layer perceptron projector that convert these embeddings, map these embeddings into the Llama embedding space. And then the Llama 2 7B model outputs tokens, which is later detokenized using a custom action detokenizer into a 7-dimensional robot action space with 3 dimensions in position, 3 dimensions in row pitch yaw, and then gripper command dimension. So this architecture allows some level of generalization, and um, so um, it uses like a unified action space for all of its training data set. So it outputs into this consistent 7-dimensional action space. And next slide, please. So because of like the Dino v2 and SIGLib backbones, it's able to capture spatial and semantic and also language information, which enables OpenVLA with some generalization ability. And during the author's experiments and evaluation, they found that OpenVLA performs better on multitask, multi-object tasks that require language grounding. And they compare that performance with Octo and diffusion policy. And they also mentioned that OpenVLA has trouble with zero-shot generalization to unseen robot embodiments, which is something that requires more research and experiments to see the limits of OpenVLA's generalization on that front. And in terms of our evaluation, can you go to the next slide, please? And currently, we have evaluated the quantized 8-bit VLA model on USC CLOSIM dataset, and we've got average MSE per timestamp around 0.1 to 0.25, which shows there's some level of generalization, even though the performance is weaker compared to some of the evaluation the authors did. And for the next steps, we're planning to evaluate the OpenVLA model on the full-size model on other out-of-distribution datasets that weren't trained in the pre-trained model. And we pretty much divided the out-of-distribution datasets into 4 categories by action space. So there's the action space with 7 dimensions that's similar to what OpenVLA already has, and then there's the lower dimension action space with, for example, only the 3 dimensions of positions and then gripper command, or the second category is um, action space with lower or similar but different features. For example, one type of action space encoding can be position and then rotation information in quaternion instead of row pitch yaw. And then another category is when the action space actually has higher dimensions. So after after we evaluate on these categories of action space, data sets with these categories of action space, we're planning to move on to vision language tasks evaluation as well. So currently, that's the state of OpenVLA effort.
Awesome. Thanks, Locke. I'll actually take the next slide to just quickly motivate the path forward in multinet. So as you know, as you just saw, the team has been doing a bunch of work in multinet, and the first step is obviously completion of this profiling effort, and we do want to release the results as a paper and a benchmark, to kind of like interact with the broader community, receive feedback, and iterate on the versions of our benchmark. And once we're done profiling these models on OpenX, we do want to move on to vision language. Awesome. Thanks, Locke. I'll actually take the next slide to just quickly motivate the path forward in multinet. So as you know, as you just saw, the team has been doing a bunch of work in multinet, and the first step is obviously completion of this profiling effort, and we do want to release the results as a paper and a benchmark, to kind of like interact with the broader community, receive feedback, and iterate on the versions of our benchmark. And once we're done profiling these models on OpenX, we do want to move on to vision language and see, how models like OpenVLA and JAT, how much of the vision language knowledge do they actually retain, despite pre-training with other modalities and fine-tuning on a completely different distribution of data. Um, and then after that, we also do want to, test these models further and see, apart from vision language and OpenX, how do they do on a more diverse set of robotics and RL data, all of these data sets which are part of multinet. And eventually, as I motivated earlier, I think we do want to take OpenVLA and try some fine-tuning experiments where we can, fine-tune this robotics fine-tuned data and model on high-quality multimodal data to see if we can achieve, an initial version of what could be a good multimodal generalist model. But yeah, that's it for multinet. I think the next slide has some contact information. So if any of you find this interesting, please feel free to reach out.
Okay, thank you very much, Pranav. So my name is Sid. I'm the lead for the cooperative robotics project. Cooperative robotics, it's sort of a general term. It means any multi-agent system of robots where they cooperate on some global task. Now, we've touched on this earlier, but robotics is sort of embodied intelligence, right? It's embodied AI, and it's the sort of link between the physical world and digital world. And so it has almost limitless applications. And so you'll notice that a lot of our projects have robotic spin on them. And, the cooperative robotics is no different. It is sort of the multi-agent extension of that. In particular, we're looking into a subset of cooperative robotics, swarm robotics. And Ben, if you would take it away and explain what that means.
Hey, hello. So, as Sid just mentioned, in this project, we want to leverage swarm technology. And so swarms are a subset of multi-agent systems with three characteristics. They have a large number of agents. These agents are cooperative rather than competitive, and they exclusively do local sensing, communication, and computation only. Next slide. Right, so the domain of our project is the in-space assembly and manufacturing market. And this market is growing across multiple industries. In particular, we can note that the large structures category, which is shown third from the top of each column, is consistently one of the most prolific and quickly developing industries in this market. Next slide. It's predicted that in-space assembly or construction of large structures, which is represented in the top right of this graph, we believe it will eventually become one of the largest markets of the in-space economy. And we believe it will become a necessity to facilitate exploration, resource acquisition, and extended habitation of space.
Excellent, Ben. Thank you very much. And so, on that note, applying swarm robotics to in-space assembly and manufacturing has several notable benefits over using single-agent architectures or singular robots. In particular, multi-agent systems have parallelization. So because you have multiple agents, they can do multiple tasks at once. They can also cooperate on tasks that are impossible for a single agent to do alone. And they have fault tolerance. If one falls, others may rise to take its place. In the case of a single agent architecture, if that single agent gets irradiated or destroyed by some micrometeorite or these days some piece of space debris, it's gone. Your mission is done. In a multi-agent architecture, that may not be the case. However, the more agents you have, you get these advantages, but there's one major drawback, which is the computational cost. So traditionally, multi-agent architectures have been approached in a centralized way. There's sort of a captain, and then there's some lieutenants or soldier robots, and the captain does the planning. But the larger the number of agents, the worse this computational cost scales with those number of agents. In particular, in cooperative tasks where they have to work together and are therefore coupled. For example, dynamically coupled. Let's say two robots are lifting the same object, then the actions of each robot actually impacts the state of the other robot because they're connected through the object. And so the computational cost can actually combinatorially explode in these centralized cases. Now, the three sort of restrictions or characteristics that Ben mentioned earlier, they define swarm systems. And swarm systems have better scaling laws because of the locality of the computation, sensing, and communication. However, they can be hard to design. Okay, so the second sort of preliminary piece, we spoke about the potential of swarm assemblers for in-space assembly and manufacturing. The second sort of preliminary piece, this parallel development of technology that's happening right now, is this idea of voxel-based modular space structures, or more generally, modular space structures. So launch costs are the highest sort of source of cost for any sort of space mission. In particular, it's the fuel cost of putting an object into orbit that is prohibitively expensive the more heavy that object gets. So therefore, it's infeasible to actually build large space structures on Earth and launch them into space. And this has been known for a long time. Space structures have always been modular. Space stations have always been assembled. However, there's a growing interest in this sort of reconfigurable modular space structure. In particular, modular space structures that are constructed from identical polyhedral modules that connect at their faces. So the most common example of this would be cubes. If you had a set of cubes, each with different components on board, you could mix and match them to serve different functions. That's the picture on the right. That project is called MOSAR. It's from it's a European Union project. And there's a sort of similar project that's shown on the left, which is a NASA project. And this one uses a shape that I'm not sure of the name of, but you can see that it's another regular polyhedron. However, both of these modular space structures, these reconfigurable structures, are reconfigured using these inchworm-style robot arm manipulators that connect at one point and move another module. And so they move modules one at a time. Therefore, reconfiguration is very slow, and they can only reconfigure. They cannot assemble the structure in the first place. They cannot bring the objects together because these arms have no propulsion. And so our problem of interest is to, motivated by these two sort of things, swarm assembly agents, a swarm of assembly agents, and a modular space structure composed of voxel modules, our problem of interest is to bring these two things together. We want to find a control input or design an algorithm to allow a swarm of agents to assemble and reassemble a modular space structure. And so that's going to involve a few pieces. That's going to involve the development of the algorithm itself, but it also will involve some physics work because we'll have to derive the dynamics of these modular structures. You can imagine that the dynamics will change as the structures get connected to each other. And all of this is to basically take a modular space structure from an initial state to a desired final state. And so that is our sort of latest project in this cooperative robotics direction, the swarm assembly of modular space structures. We've recently published we've recently put out two overview documents. One is for cooperative robotics in general, where you can gain some additional context. The second is for this project in particular. In that project overview, we also have a more rigorous sort of problem definition, so you can see the details. And if you have any questions, feel free to reach out to me or Ben. Okay, thank you. Moving on to metacognition.
So I think Thomas will take over for this one. You want to move one slide forward, Sid?
Yeah, so on the metacognition front, this is a very, can you answer me?
Yeah, we can. We can.
Oh, okay, my thing wasn't lining up. So on the metacognition front, we have a very early project that's focused on calibration error in models. And so what is that? Calibration error is basically, trying to measure a model's understanding of its own accuracy. I might query a model for some information and it might give me back information. But along with that information, I'd like to know, how confident are you? What is the probability that you are correct? This is very important, I think, across domains. I think just for straight language modeling, you're interested in this from the perspective of hallucination, reducing hallucination. I want to know if my LLM is giving me good answers. And if the LLM can provide feedback on how confident it is, then that's very useful. It's also useful in the context of something like robotics. If you're doing something very, very important, say assembling a structure in space, and a robot becomes uncertain about its actions, that's important. You might want to take action. You might want to take it over to a human being, ask a question. We're also interested in this from the perspective of exploration. So uncertainty-driven exploration of say reinforcement learning policies or action spaces is also of great interest. So very very early project here. Our initial focus has been on LLMs, kind of with an aspirational intent for multimodal action models, VLAs, that kind of thing, and of course eventually robotics. But initial experiments have been focused on LLMs. It's a fairly simple data sets, and our initial experiments have shown a signal here, which I think is really, really interesting and kind of mirrors, I think, what's been found in literature. It's not a super strong signal, but it's there, and I think we would like to explore it, understand it, and make it better. So I think these initial experiments are going to be focused on techniques in metacognitive prompting to see if we can tease out a stronger signal for calibration, model calibration. And then we also want to ask questions like the relationship between system 1 and system 2 accuracy scores. So is the model sort of manually reported accuracy correlated with or better or worse than, say, trying to extract a measure of confidence from logic probabilities. So all of these things are of interest. But like I said, very, very early. So frankly, maybe a good project to hop in on because we're kind of at the start. But yeah, I think that's where we are here.
Thomas.
I'm Thomas, by the way.
We have one question in the Discord chat asking for a clarification around what is precisely being measured here. So can you just go over that again?
Yes, of course. So I'll explain by example. Let's say I ask a model, what is the what is the capital of Massachusetts, and it says Houston. What I would like to understand, or what I would like the model to then give me, is along with that answer an associated probability. So hopefully it gives me a low probability, say 20% 20% probability of being correct, or maybe it says Boston, and it says 95% probability of being correct. And this is sort of, the intent is to mirror like say a human's ability to report their own accuracy. So let's say I know nothing about calculus, and nevertheless I'm given an integration problem, and I make my best effort, but I know nothing of integration. I could probably tell you like, hey, like here's an answer, but I'm not confident at all. So it's 5% probability of being correct, 0% probability of being correct. And so perfect calibration would be basically the model's reported probability of being correct about any given fact is in perfect agreement with the actual observed probability that it is correct. Hopefully that makes more sense.
Yeah, thank you. So yeah, please reach out to Thomas, myself, Helen, Lou, regarding this project if you're interested. I think this slide covers that. Yep. Great. Awesome. So we're going to move into some earlier projects. Some of the more nascent ones, or the ones that are emerging, the ones that we plan on launching soon. We've had questions about a couple of these, and we have a couple other ones to share as well. So these kind of projects run the border between a fully realized project at Manifold, which has dedicated resources and people, versus more of an interest group. And you'll kind of see they kind of form as they go. So let's go ahead and go one slide forward. So one of the interesting topics that we are planning on tackling very soon, and we sort of have formal sponsorship to do this, is to try to understand how you can build more effective learned mappings to be able to dynamically control software. And I'll talk about the problem formulation for a second here. One slide forward, please. So this notion of tool use. A lot of teams have been thinking about this, and most approaches sort of map traditional foundation models to working in trying to interact either with APIs or with graphic user interfaces. State of the art in the API space is what's referred to broadly as function calling, and more recently, people have started to develop approaches to multi-step function calling. Reliability is still relatively low, both on benchmarks and in practice. You can check out the Scale AI tool use leaderboard. You can check out Gorilla. Single calls in specific programming languages being done by LLMs is, of course, that's totally within domain, and they do really, really well on that. But you see a pretty big reliability breakdown as you propagate the probabilities of success through multiple steps. And we also are exploring fundamental limitations here. So a lot of function calling and sort of tool use as defined by function calling happens in context. So you end up with some brittleness in how an LLM might be able to tackle, or a VLM might be able to tackle, a specific workflow. You also run into the issue of these workflows not being inherently multimodal. So, the model's not inferencing over what the underlying payload is, if it is some sort of multimodal operation, or if something like that matters in the workflow. So there's sort of limitations in how you formulate effective use of cloud tools or local tools in the function calling way, at least as it is today. The other side of this is that we don't have a slide for this, but if you look at sort of state-of-the-art work in user interfaces like getting sort of models out of the box to work with manipulating user interfaces in the way that a human would, right? Through keyboard entries and mouse clicks and sort of clickstream trajectories and things like that. The performance is also similarly low. So I think the state-of-the-art work. The state-of-the-art work in that area is OS Worlds, and so that's worth checking out as well. One slide forward, please. So one area that we're exploring is the use of vision language action models, which we described in detail in the multi-net and multimodal action model section, as the basis for effective transfer between these kind of action and control domains, often which happen in 2D, or they could be 3D robotic simulation, and what we think of as actually a pixel space control environment in the form of a graphic user interface based workflow on your local machine, or long trajectories of action sequences. One slide forward, please. So this kind of is just a brief, simple visual that compares these kinds of trajectories. So we view these all as trajectories problems, and we actually see a lot of similarities between the traditional sort of robotics and control problems, where you're in environments with potentially incomplete information that are evolving, that require your agent to be interacting with different black boxes to achieve different kinds of objectives, and where objectives can be accomplished in different ways. There doesn't necessarily have to be a specific trajectory, but there can be a variety. Oftentimes, those objectives are structured in a rewards-based scenario. And so we kind of think about the sort of the two scenarios underneath the graphic user interface based trajectory and the sort of API trajectory as more similar to this robotics framework versus the traditional just next token prediction framing. And so we are exploring in the very early days transferring some of the VLA work we're doing to this problem domain. And this is actually also formally supported by one of our only spin-out Medarc, which is working in the same domain. Do you want to move one slide forward, please, Sid? So yeah, if this project is just spinning up, it will, the multinet team is still sort of focused on multinet, but in the future we will start to look at this. Please reach out to Pranav or I about getting involved here. And this is a formally sponsored project. So we're thinking about what are new benchmarks in tool use. So the benchmarks in this area are super underdeveloped, especially as it maps to the new formulation that we're describing here. What are the approaches? Like how effectively can you fine tune some of the VLAs like Open VLA that Locke was discussing a little while back, and building some new models as well on top of the other multimodal action models that we're designing. So super excited to launch this very soon. And I know there's been a ton of interest, so I wanted to give a little bit more information, and please reach out if you're interested in getting involved. Helen, I think this is all you.
Okay, hi everyone, I'm Helen. So one exciting direction with vision language action models is actually vision language probing. Probing involves training a classifier on the frozen representations from a pre-trained model to evaluate how much high-level information is encoded in the model's representations. So the illustration on the right shows an instance of semantic probing, where the probe predicts a representation of the world based on a language model's embedding. And the representation is updated when the discourse describes changes to the entities in the world, their state. So we want to do something similar, but on vision language action models. And probing is useful because it allows us to track the model's understanding of the world's state as it changes. This not only makes the model more interpretable, but also allows for better interfacing with other systems. So we can then augment the model with other components such as long-term memory, and we can also fact-check the model's understanding with other knowledge sources. And this will enable us to form a coherent understanding with the probe's predictions and other knowledge sources. The next slide. And a next direction with VLA models is also we want to evaluate these VLA models with real robots. And as some preliminary research has shown, VLA models are actually, they don't perform well directly out of the box. And which is why we want to then better evaluate them, get a more comprehensive understanding of them, as well as evaluate them in the real world on physical systems such as the Kinova arm, the Fetch robot, and the Boston Dynamic Spot, which we have access to currently. And also, Harsh, do you want to say something about evaluation in the physical world?
No, yeah, you actually covered it very well, Helen. Thank you. So I'll just say that this is super early and this is super difficult, right? One of the hardest things in robotics, I'm sure as many of the roboticists in the audience know, is actually evaluating how well your policy is doing, how well your embodied agent is doing. It's one of the reasons, like the reason multinet is offline is because it's basically impossible to get these things set up. But we are doing so anyway. So I think this is the very early days of us trying to set up partnerships with some of these labs. So, Helen at Tufts, and Helen's also a member of the core team. We're looking into potentially seeing if we can get some of these robots set up as evaluation environments. And so if you have any connections, if you have robots, if you, preferably those within OpenX, but otherwise also more broadly, or if you have sort of in network connections to groups who might be interested in sponsoring some of this. We're very interested in trying to set this up not just for ourselves, right, but for the entire community, because these VLAs are becoming a more and more key piece of what looks like the future of action-oriented AI and especially robotics. And so it's important to be able to try to build reusable pieces of infrastructure that allow for relatively fast evaluation and realistic evaluation, right? Everything can't just be offline. And everything, you can't just buy you don't have to buy a $500,000 robot to test your model, right? So it's very early days, but please reach out if you have connections or resources or ideas on this front. We would love to hear it. I think we can move forward. Cool. Luke, I think this is all you, my friend.
Thank you, Harsh, and nice to meet you all. I'm Luke, member of the core team here, and very excited to announce a new group that we're spinning up here in terms of generative biology. So you all may have seen, some of the BioML models that have been, released, like AlphaFold 3, and the ability to generate synthetic chemicals to support in drug discovery and a variety of other initiatives. This space as a whole is relatively new, opposed to large language models, and there's just a lot of long-term growth and capability available. So we're putting together this group to initially understand the space of these foundation models being used in biological applications, as well as the state of AI in medicine and synthetic biology today. We're still in an exploratory phase of this group, mostly reviewing literature, analyzing the open source landscape. And this has also traditionally been, I'd just like to note, more of a siloed space. So there are a lot of open source heavy AI specializations like large language models, natural language processing, but this is one historically that has been quite siloed, you could say, in terms of like pharmaceutical companies and not really having that developed of an open source community and data set. So some of our aims also include just to optimize research methods available and then refine our research directions over time. In Q2 of 2025, we're aiming to take an existing open source BioML model and optimize it, also publish some analyses, so get an understanding of open source and closed source models, how they perform against key benchmarks, as well as the open source data set landscape. Again, this is an area where we don't really have a lot of data available, and it'll be key, especially as we look into eventually putting together our own open source model in the space of really profiling all of the available data and putting together our own data set within Manifold that we can use to train that model. And then also by Q2 of 2025, we're aiming to finalize our research directions as well as our team. Did also just want to note we're actively recruiting additional team members. So if this is of interest, please let us know. You can reach out to Harsh or I. And then moving into the longer term, Q4 of 2025, we are aiming to have a couple of publications, one of the open source model optimization work that we'll be doing soon, as well as a survey of the synthetic and generative biology space. We also, at this point, want to actively be implementing each of our finalized research directions. So we'll likely have different subgroups, those that are focused on synthetic biology more broadly and medicine, and then perhaps those who are maybe more focused on drug discovery. There's still a lot of possibility here, but those are just a couple of directions that we could take based off of our initial research directions. And as a part of this, we'll have our timelines finalized, and then also emphasize novel research methodologies as part of this longer term research within the group. So we want to explore new ways that we can improve these models, new experimental techniques, new ways of training the models, putting together the data set, and utilize that in providing more value to the space. So again, very excited to be spinning up this group. And if this is of interest to any of you, please let Harsh or I know. And Harsh, not sure if you had anything else that you wanted to add to this as well.
No, that was awesome, Luke. Thank you.
Okay, thank you, Luke. So, folks, I hope you enjoyed those updates from our research projects. Very exciting progress happening. We also have some exciting progress from the organization side. So, we have some teams that are recruiting. So, first, I'll touch on the operations team. We're currently looking for a digital artist or a graphic designer, somebody with experience in that sort of domain. But in general, the operations team is recruiting. We are responsible for external facing materials, for example, the research log, as well as the website. We also take on event organization like these community research calls. We have a series of new events that we're also starting, including one that I'll touch on that we've already started. I'll touch on that in the next slide. But that's also an exciting area that operations is involved with, and much, much more. Operations essentially ensures the smooth running of Manifold research. On the project side, each of the teams touched on this, but multinet, multimodal action models, the swarm assembly of modular space structures, and the tool use projects are all recruiting right now. We're looking for collaborators. So feel free to reach out, ask any questions you may have, or you can apply to the OS team. The application is on our website, and those links will be shared after the call. And also, very excited to explore those emerging focus areas that we talked about. Touching on the events briefly, I had shown this slide in Community Research Call number 2 back in July, and I'm showing it again because we are on schedule here. So at that time, we mentioned that the community research calls were started, and we had the Frontiers talks and the reading groups planned. Now, we've also had the first Frontiers talk. That's also started. This is our seminar series where speakers are talking about their cutting edge research, and we have a few lined up. So I'm very excited, and we're very proud of that. I'll touch on that in a little bit more detail here. So, like I mentioned, this is our series where we bring in top researchers, engineers, working on the cutting edge in various fields. It does not necessarily have to be in the same fields as the Manifold projects are. It can be much more varied than that. The first talk that we had was from Helen. That was on September 30th, and the recording is available on our YouTube channel. The recordings will always be available on our YouTube channel, by the way, for the Frontiers talks as well as for any updates, any events. And we have 3 more Frontiers talks planned to close out the rest of this year, including the next one, which will be on de-identification of student records and student writing for the purpose of creating large educational data sets that we can train educational models on. If you want to learn more about any of our upcoming events, you can feel free to check out manifoldrg.com/events, where new events pop up there automatically and you can see the descriptions of them. You can also see records of our past events as well as the recordings there. And subscribe to our Luma calendar to get a ping for or a notification for any time a new event is announced. Okay. If you want to get involved, there's more ways than just joining these community research calls. You can also subscribe to our mailing list. We'll let you know directly via email about upcoming events, as well as you'll receive our research log, which is our bi-weekly publication that tells you the latest updates from our projects. And we also include updates from more than just Manifold, other exciting updates across sort of the field of intelligent systems. That section is called the Pulse of AI, and Luke works very hard on that every other week. So, you know, it's a high quality and good publication. I think I enjoy reading it every time. The other thing that you can do is you can check out our GitHub to see ongoing work. We regularly have open issues hosted there, and there you can read the comments and threads, and all of our work is public. And so you can see sort of the real-time progress of these projects. And of course, if you're interested in working more closely with us, you can join the OS research team. The application for that is on our website as well. Again, the links will be shared. The OS research team is a committal role. You don't have to be part of the OS team to contribute. Those that are part of the OS team are volunteering and committing 10 hours a week to work on Manifold research projects. Okay, thank you all so much for attending today. I hope that you enjoyed this community research call number 3, and we're looking forward to seeing you guys in the next one. We're going to host these quarterly, so they'll always be jam-packed with updates and new ways to get involved and new projects and other exciting things. So thank you all very much. Any parting words, Hirsch?
Yeah, real quick, I just want to say, guys, we ran a little bit over this time. Apologies about that. We try to keep these in the hour, but we're an hour and 10 today. And some of the speakers have had to go to other things. So if you have questions, I know we tried to answer some during the talk, but I'm sure many people have more questions. Please send them in the Discord. We will be able to answer them. Everybody, all the different leads are there, and they will definitely be able to answer them. And you can see all these projects, so you can go to the specific channels. Looking forward to seeing you there.
Thanks, y'all. Have a great rest of your day.